Hello everyone, welcome back to our system design channel. So in this video we are going to continue talk about the key value store design on a single node. Especially in last video we talked about the right path of the key value database based on the log structured merge tree. If you forgot the previous video knowledge, then please go back to the previous video. I also attached the link to the previous video in the description of this video. Okay, cool. And let's have a brief retrospection. So in previous video, we talked about how to use the log structured merge tree to do the right path for a key value store on a single node. Okay, so the two concepts are log file, MemTable, and the SSTable. So basically, when a write request comes, we have two steps. First, we append the new key and value data to the end of the log file on disk, because append means we are continuously writing the data to the same file. So we have the best performance on disk, right? And the second step is after writing the data to the log file on disk, then we are going to write the data in the MemTable, which is in memory. It's a B tree or it's a binary search tree, right? Which means the data is stored in memory, sorted by their keys. Okay, and after we write the data in the memory, then we return to the client to say, oh, you have a successful write. Okay, cool. And also we talked about when the memory becomes full or it exceeds our maximum allowed memory storage. For example, you could say, oh, once the MemTable becomes 10 GB, then we are going to flush the data to the disk into a new file. And this file is called SSTable. Okay, and when we flush the data, because the data is already sorted in the memory, right? So we will write the data to the SSTable file. They are also sorted based on the keys. Okay, cool. And also we talk about in different SSTable, you could have the same keys, right? But only one of the SSTable, which is the latest flushed SSTable, will have the latest value of the key. Okay, so that's the right path which we talked previously. Okay, now let's talk about the read path. Okay, cool. So now let's see, we are going to read the data whose key is this. Okay, and now let's see, the request comes to our machine. Okay, and we also talked about we have in-memory data and we have the on-disk data. Okay, so this is the read path. Okay, cool. So we have the in-memory data, we have the disk data. Okay, the first thing. Okay, so here let's remove this log data, because log file is not rated on read path, but SSTable is. Okay, so now let's see, we have this SSTables. Okay, cool. Now let's see, the key we are going to read is, the key could be a string or it could be a number, right? But anyway, you can sort the data for strings and values, right? In our example, because we started in previous example, our key are numbers. So in here in the read path, let's say the key is also a number, which is 78. Okay, cool. Now let's see how it works. First, we are going to check our MemTable to see, okay, whether in the MemTable, in the in-memory data structure, we have the key and value for this 78. Okay, so if we have the data in memory, it means, oh, we have the latest data in memory, right? Because it means some previous write have written this data or updated this data with latest data in the memory, right? Remember, in-memory table, MemTable always have the latest data if it has. Okay, so okay, now let's check the MemTable. Yes, it indeed has this key. Then we just return the value of this key to the client. Okay, so this is very simple. Okay, so now the problem is, what if the MemTable doesn't have this key? Okay, So in this example, let's say we in the MemTable we don't have the key for 78. So it means it could be on some SSTables on the disks, right? So in our example, it indeed exists in both SSTable 1 and SSTable 2, right? So the thing is, if it's not in memory, what we have to do is, we have to read SSTable 1, and also we have to read SSTable 2. Let's say we also have other SSTables, okay? So let's say we also have SSTable 3 and some others. So you have to read all the SSTables to get the key 78's value, right? So how we are going to read all the SSTables? The naive way to do this is, yes, you just read all the file, get the whole file's content in memory, and then scan the whole content and check the key, right? So you would imagine it's very slow, right? Especially we said the reason why we have SSTable is because we don't have enough memory for the MemTable previously. So actually there's no way you can read this table into the memory, right? Okay, so in that way, how we are going to do that? Okay, so we are going to use there are several optimizations, okay? The first optimization is, let's say, which SSTable tables have the key, okay? So let's say, okay, this is SSTable 3, okay? So now let's say its key is 173, and let's say 600, okay? So this is SSTable 3's data, okay? Cool. Now we can see that the key 78's data is in SSTable 1 and SSTable 2. It's not in SSTable 3, right? So how can we quickly check which SSTables have this key? So we don't need to read other tables, right? So the way we are going to do this is called Bloom filter. Okay, so what is Bloom filter? So first, each SSTable will have a Bloom filter. Bloom filter, you can think it as a long bit array. Okay, so let's say each square here is a bit. Okay, cool. So here is bit 1, here is bit 2. Okay, so it's an array of bits. Okay, so it's an array. So cool. So let's say this is a long bit array. Okay, this is a bit array. Okay, cool. So now when we flash a key, when we flash the MemTable data to a SSTable, we have the keys, right? So for each key, we will perform this operation. So for each Bloom filter, we have multiple hash functions. So let's say we have 3 hash functions. So this is function 1, and this is hash function 2, and this is hash function 3. Okay, so let's say we have 3 functions. Hash functions. The hash function will map a key to a position in the bit array. So now let's say we stored the key 67. Okay, so now for key 67, when we write this key's data to this SSTable 1, we will run the 3 hash functions for this key. So let's say the hash function maps the key. Hash function 1 maps the key to this position. Okay, cool. And hash function 2 maps the key to this position, and hash function 3 maps the key 67 to this position. Okay, so then we will mark each position value as 1. Initially, all the bit array is initialized as 0. So here we mark it as 1. Okay, so this is also 1. Okay, and this is also 1. Okay, cool. And for the key 78, when we write it to the SS table, we also run the 3 functions, and then it maps this key. So for example, hash function 1 maps 78 to this position. So similarly, we mark this position as 1, okay? And also hash function 2 maps it to this position. So this position will also becomes 1. Okay, cool. Let's see hash function 3 maps it to the same position as the first one. Okay, so it also maps to this position. So this position is also marked as 1. So we do nothing here. Okay, cool. So now you can see when we write all the keys to this data, we set 1s in this bit array, right? So now let's say we want to check, given a key, let's say given a key X. Well, we want to see whether this key existed in this SS table or not. Then we will run the same hash functions, the same 3 hash functions to this given key X, and we map it to 3 different positions, right? So if all the positions have 1, then it means this key could be existed in this SS table, right? So because let's say if key X, okay, this is the first case, right? So let's say after hashing the key X, the given key X to the 3 positions, okay, let's say the first hash function maps the key X to this position, okay, it's 1. And the hash function 2 maps the X to this position is 1, right? And also it maps key X to this position, which is also 1. So all the hashed positions have value 1. It means the key could be existed in this SS table, right? Why would I say it could existed? Because it may not exist in this table. The reason why the 3 positions has 1 is because some other keys mapped to these 3 positions, and they labeled these positions as 1, right? So even key X does not exist in this SS table, the 3 positions could still have 1 because some other keys, right? Okay, so this is the first case, which is the mapped positions all have data 1. Okay, the second case is that, okay, after we map the key X to the 3 using the 3 hash functions, 1 or more than 1 of the positions could have 0. So let's say after we apply hash function 1 to this position, okay, it's 1, no problem. But after we run hash function 2 to this key X, it maps it to this position, okay? This position has value 0. Okay, then this means this key definitely does not exist in this SS table, because if it exists, then this position should be labeled as 1. But now we see, oh, it's 0. So it means this key definitely does not exist in this SS table. Okay, so now with this, you can see, okay, with Bloom filter, which is essentially a bit array and several hash functions, we can quickly check whether the key does not exist in a file or in a table or not, right? Because if one of the hashed function has value 0, then it definitely does not exist. So with this, we can filter out SS tables which does not have this key, and we only check those SS tables which potentially have this key, right? Okay, cool. So now let's say with this, let's summarize it. Okay, so for each SS table, okay, so here is a Bloom filter. Okay, the problem it solves is whether this SS table has key or not, has a given key or not. This is a problem it solves with Bloom filter. Okay, so and each table, each SS table have a Bloom filter. Okay, have a bit array like this. Okay, so now let's say given the key 78. Okay, we want to see which SS tables potentially have this key. Okay, so then we just run the 3 hash functions for each table. Okay, so let's say for SS table 1 we have these 3 functions, right? So when we just run these 3 hash functions to the given key 78. Okay, if we checked, okay, one of the hash position have zero value, and then it means, yeah, this key definitely does not exist in SS table 1. In our case, it exists because the key is indeed here, right? So after we apply the 3 hash functions, we would see, oh, for key 78, all the positions it hashed to has value 1. It means, yes, we need to check SS table 1. Okay, and similarly for SS table 2, it also has its own Bloom filter. And after we apply the functions from the SS table 2, we would see, oh, all the positions, because the key 78 is in this table, the result we get is that all the positions in the Bloom filter has value 1. So which means we need to check SS table 2. And for SS table 3, yes, in reality, the key 78 does not exist here. So possibly we could get, oh, after running the hash functions, we would see, oh, one or multiple positions in the bit array of the Bloom filter will have a value 0. Then we don't need to check SS table 3. So for this request, we only need to check SS table 1 and SS table 2. But there could be also another possibility, which is, yes, even the data does not exist in SS table 3, we still get all the positions as 1 for key 78, because, for example, key 600 could also mark the 3 positions as 1, right? So in that case, we still need to check SS table 3. But as long as you have a good hash functions and you have multiple, for example, let's say you have 10 different hash functions and your bit array is very long, then the possibility would be very low that after checking SS table 3, you would see the data exists in this table. So in reality, most possibly you will only check SS table 1 and SS table 2. Okay, so now we see with Bloom filter we could filter out those SS tables which we don't need to check, right? So now this comes to problem 2, okay, which is problem 2. So in a single SS table, how do we quickly read the data from the given key? Okay, how do we quickly read the data? Because we cannot read the whole table's data. We cannot load the whole table's data into memory and then check the key, right? We must have a way to quickly read the data just from the disk for the given key, right? Okay, so how can we do that? Okay, the simplest solution is for each SS table, we could have a in-memory index. Okay, so it could be something like this. Okay, so for this SS table, for each SS table, let's say for this SS table 3, we could have a index. Okay, let's call it key index. Okay, so what does it look like? So basically it's a hash map. Okay, so here is the key of the hash map and here is the value of the hash map. Okay, so when the system bootstrap, okay, for when this machine starts up, we will read a SS table, and for each key it has. So for example, for the key 1, okay, we don't store the actual value here. We don't store the actual value of this key. Instead, we store the position of the value on this in this file. So let's say this key's position is 0 in this file. Okay, so this value actually represents the position of the data entry in the file. The position actually means the offset, the file offset. Okay, cool. And for key 173, okay, so the value is, let's say, is 64. Okay, so here, so let's say the byte position, the offset for this key 1 is 0, and for this key 178, it's stored at 64 byte position in the file. Okay, and similarly for 600, it's stored in byte 1000. Okay, so then the in-memory key index would say, oh, I would have, for key 600, I would have file offset, which is 1000. Okay, so we have this key index table. Okay, and it could be similarly, it's actually a binary search tree, or it's a B tree, because we want the keys to be sorted, right? So here, let's say, okay, for this SSTable 3, now let's say, okay, so we want to check for data 78. Okay, so then we just hit this table. We just read this table. Okay, so we see, oh, 78 is actually not here. Then we return to say, okay, SSTable 3 actually does not have this data, right? But let's say this key index table is for SSTable 2. Okay, so it's for SSTable 2. Okay, then we would say, oh, for key, it will be look like this. 56 is in position 0. For 78, it's in position, let's say, it's 128. And for this key, next key, which is 280, okay, its position in the file, the byte position, the byte offset, it's about 300. Okay, cool. So then, okay, we will read this key index table, which is in memory, right? So we found the key 78, and we know its value, which represents the position or offset of the data entry in the file. And we know we should read the data from position 128 in this file. Okay, so then we just go to read the data from position 128, which is here. Okay, and we just get the value of this key 78, and then we return it. Okay, cool. So this is the simplest way to do it, right? So okay, so let's say with this simplest way, how the read path look like. So the read path will look like this. So first, okay, the request comes, which is, oh, I want to get the data of key 78. So first it checks the MemTable, which has the latest written data in memory, right? So okay, let's say the key is in the MemTable. Then we just return the value for this 78. Okay, cool. And let's say the key is not in this MemTable. Then we will run the Bloom filter algorithm for each of the SSTable to filter out those SSTables which definitely does not have the key, right? So let's say after running the Bloom filter algorithm to all the 3 SSTables, we filtered out SSTable 3, which means SSTable 3 definitely does not have the key. And now we only have SSTable 1 and SSTable 2, right? So then the next step is for each SSTable, we are going to check their key index table. Okay, so for SSTable 1, we check its key index table. We got the position of the key 78, the offset, the file offset in the SSTable, right? So let's say we get the position which is here. which is here, okay? So then we just read the data from this position for this key 78. And also for SS table 3, similarly, we check its key index table, and now we know, okay, we must read the data from the file in this position, okay? And then we get the data from SS table 2, right? Okay, after we get the data, we will merge, because we have data from both SS table 1 and SS table 2. Now we are going to merge them, right? So we know, okay, SS table 1 has a time step, which is T1. SS table 2 has a time step, which is T2. Let's say T2 is larger than T1. Then we know the data in the SS table 2 is actually the latest data. So we just return the data from SS table 2 to the client as a result. So this is how it works. Okay, cool. Yeah, seems everything works fine, but there is a potential problem. Here you can see for each key index table, we are storing all the keys, right? So for each SS table, we are storing all their keys file position in this index table. Let's say each SS table could store tens of millions of keys, okay? Then you can see this key index table for each SS table will consume a lot of memory because each table has tens of millions of entries, right? And also considering the position, it could be 68 bits, right? And with some other metadata, the data could be exploited very largely, right? So in reality, possibly there is no way for us to store all the data, all the key index store all the keys of a SS table in the memory. Even we are not storing the keys value, we are only storing the position or offset in the file for the key, right? So how can we solve this problem? Okay, the way we are going to do this is instead of storing all the keys, okay, instead of storing all the keys in the SS table, we are just going to store some samples. Okay, so how does it look like? So let's say we store the first key 56 and we store its file offset, which is 0, okay? But we are not going to store 78. Okay, so we are going to store samples, which is, let's say this file has more data, okay? So it has more keys here, and then we also have key 3000, okay, and we have its value, okay, and we have the key, more keys here, and we have key 10k, 10k, okay, and we also have value, okay, cool. So we are going to store the data in a sampled way. So here in the key index table, we are going to store 60. Let's say for table SS table 1. So let's say this is a key index table for SS table 1. Then the key could be 68. And we know the offset is 0. But we are not going to store the key 78 and 108. We are 190. We are just skip it. Let's say we skip for every 100 keys, okay? So after 100 keys, we see, oh, now the key is 3000. So we just store the 3000 here, okay? And we know the value, which is a file offset in this S table 1, right? Let's say it's 4,800, okay? So we know the position, and also the next key could be 10k, okay? And the offset is 2488, okay, so let's say it's like this, okay? So we only store samples of the keys in this key index table. Okay, cool. So this is in-memory key index table, right? Okay, cool. Now let's move this away to the right, okay? Because now we are only going to talk about a single table, right? So here we also have, so our previous index table now will be on disk. Okay, so now let's say we have a key index table for SSTable1. Okay, so here we are going to sequentially store the data here. Okay, so for each row of this file, of this key index table, or let's say it's just a key index file, okay, for SSTable1. So each row of this table has two parts. The first part is key, okay. The second part is file offset. So basically it's we're just moving the previous key index table in memory, which has all the keys, into a key index file. So instead of storing all the keys in a in-memory table, now we are storing them in a disk file. Okay, so for each row of the file, we have two components. One is key, so which is 67, let's say 78, 188, 190, and similarly the second part is file offset. Let's say for 78, the file offset is 33, and for 190, it's 48. Okay, cool. And also for 3000, the offset in the SSTable file is, let's say 4,800, and okay, between 190, there's a lot of other keys. Okay, and also between key 3000 and 10k. Okay, there's also a lot of other keys, and also for 10k, the file offset is this. Okay, cool. So now we are storing all the keys file offset in the SSTable in this new file. Okay, so this is a new file. Let's say we call this new file as key index file. Okay, and now let's call this and for this one, for this key index table in memory. Okay, so now let's rename it. Let's call it as key summary table. Okay, cool. And now the value for this key, for the key here, so the keys here are only a sample of all the keys in the SSTable, right? Let's say we get a key from the SSTable for we only store every 100. So for every 100 keys in the SSTable, we only store the first key in this key summary table. So let's say we stored key 67, we stored key 70 or 3000, and we stored key 10 key here. Okay, so the value here for the key is the position of the key in this key index file. Okay, so let's say this is 0, and now let's say this is, let's say it's 320. Okay, now let's say this is 3800. Okay, so the position here, this 0 points to this table, now points to this key index file. Okay, and this 320 points to this position in this file, and this 3800 points to this position in the file. Okay, cool. So now let's move this to SSTables on this side. Okay, cool. So now the value in this key summary table represents the offset in this key index file now. Okay, so now let's say we have key, our request still requests the data for 78. Okay, now we are going to read the SSTable1's data, right? So first we are going to check this key summary table. Okay, we know 78 is between 77 and 3000, right? So the data must be between these two keys, right? And we also know the file offset between these two keys in this key index table is 0 and 320, right? So then we just read the data between this 0 and 320 in this key index table, right? So we read the data between 0 and 328, which is this record here, right? So we read all the keys from this range, which include 78. Okay, and also after we read this data, okay, because here the data we read is very small, it's only 320 bytes, right? So, okay, we get all the keys from this key index file, all the keys here, right? And 78 is one of them, right? And for 78, we know the file offset is 33. And this file offset points to this file, SSTable1, right? So here, let's see, so this file index points to this table, right? And for 32, it points to this position. For 68, it points to this position, right? Okay. Let's use a different color to distinguish them. Okay, cool. So now we get 78 from this key index file. We know the file offset in the SS table is actually 32, right? So then we just read data from this position, which is 32. Then we get the value for this key, right? So then we return it to the client. Okay, so with this, you can see, because we are not storing all the keys and the offsets in this SSTable1, we are only storing a sample of the keys in this key summary table. So this will consume very small amount of tables, right? And also we store all the keys and their file offset in the SSTable in this key index file, but this key index file is only on disk, so we have more space on disk, right? And also when we read the data from this key index file, we are only reading a small part of some small bytes from it, right? So for example, let's say for 78, we know it's between these two keys, so we only read the data between these two, between this 0 offset and 320 offset, right? So we only read 320 bytes from this key index file. And for this one, 380, so I think it shouldn't be this large, right? It should be only 340, okay? So in reality, we only store the offset for every 328 bytes, okay? Cool. And with this, okay, we know the key summary table for each SS table actually only consumes a very small amount of memory. So this resolves our memory problem, right? But now we have a key index file for each SS table, but it's large, but there's no problem because it's on disk, right? Cool. So now with this, let's go back to have a retrospect of what the read path look like, okay? So first, we are given a key, which is 78. First, we are going to read the memory table. Okay, we say, oh, the data is in memory table. Then we just return the data, return the value from the MemTable to the client. Okay, if in MemTable we don't have this key, then we are going to apply the Bloom filter algorithm to each of the SS table to filter out those tables, those SS tables which do not have the data definitely. Okay, cool. So for the remaining SS tables, we are going to run this key summary table. Okay, so now let's say the data could be in SSTable1. Then we go to check the key summary table for SSTable1. Okay, cool. And we get, okay, we know 78 is between this key and this key. And we know the offset for these two keys are 0 and 320. So we are going to read the data from the key index file for SSTable1 between these two offsets, okay? And between these two offsets, oh, we now get all the keys here, right? And one of them are 78. And we know, oh, for 78, the offset for this key in the actual SS table is 32. Okay, now we are just going to directly read this SS table based on offset 32. And then we get the actual value for 78. And then we just return the data. Okay, and after we read the data from different SS tables, we are going to merge them based on the latest time step, which represents the latest data, right? And then we are going to return to the client. So this is the read path, okay? So, is there anything we can further optimize here? Okay, cool. The first thing we could optimize here is, okay, so for some of the data, we could do some caching, right? So for example, we know, okay, 78 is frequently or maybe latestly accessed, right? So then we are just going to store the offset in this SSTable1 to this, for this key 78 for its offset, right? So we call this as key cache, okay? Let's see, we have a in-memory cache, another in-memory cache, which is key SSTable key cache, okay? What does it mean? It means it's a cache for storing the offset of a key in this SS table. So let's say we have the key and we have the value, which represents the offset in SS table. Okay, cool. So now let's see for 78. Okay, let's say recently we queried 78, and we know its offset in this SS table is 32. Okay, then we are just going to store 32 here. Okay, so next time when a request comes to request 78, now instead of going to check the key summary table and then read the key index file, we are just going to get the data from this cache. Okay, we know, oh, 78 is here. We know the offset is 32 in this SS table. So then we are just going to directly read this SS table instead of going to check key summary table and the key index table again. Right? So this is how we optimize this with SS table. And furthermore, let's say SS for the key 78, it's very hot in the last 1 hour or something. Let's see, every user will query this data. Then instead of just storing the offset in this cache, we can have another cache, which is, okay, hot data cache, right? So we are just going to store the value, the actual value for the hot key 78, and it could be a employee JSON string or something right here. Okay, so because it's a hot data, so let's say later when another request comes, we first check this hot data cache. Oh, we know, okay, it's in this hot data cache. Then we just return the value for this key, right? Cool. So this is this video. Thank you for watching and see you next time.